We have already studied the parallel plate waveguide for the transverse magnetic mode. Now in this video we are going to study the parallel plate waveguide for the transverse electric mode. In the transverse electric mode, the electric field, the longitudinal electric field Ez equals 0, and the longitudinal magnetic field Hz does not equal 0. So the longitudinal magnetic field Hz can be represented as the mode function Hz as a function of xy multiplied by the propagation wave or propagation function e to the power minus j beta z. And once again, due to the continuity of the field in x direction, the field is independent on x direction. It depends only on the y direction. So in this case, the derivative with respect to the field in x would be 0. So the reduced Helmholtz wave equation can be represented as partial squared by partial y squared plus kc squared hz as a function of xy equals 0, where kc equals square root k squared minus beta squared. And as we mentioned, the general solution for this differential equation can be represented as an unknown amplitude A sine kcy plus another unknown B multiplied by cosine kcy. So we have a function sine and the other function is cosine. And once again, it is required to determine the amplitude of these unknown functions or of these unknown amplitudes, and also it is required to determine the cutoff wave number kc. In the present case, we cannot apply the boundary condition directly on Hz because the boundary condition states that the tangential electric field component on the conductor would be 0. But this is Hz magnetic field, not electric field. So to obtain the field component which can be used to solve or which can be used for applying the boundary condition, we should obtain or we should determine the electric field components. These electric field components in the present case are in the transverse plane because we have Ez equals 0. So it is required to determine Ex and Ey. Effectively, from the field equations of the transverse electric field component, we see that Ex is proportional to partial Hz by partial y, while Ey is proportional to partial Hz by partial x. And as we mentioned, the field is independent on x direction, so the derivative with respect to x would be 0. It means that we don't have electric field in y direction. We have only electric field in x direction. So Ex in this case would be minus j omega mu over kc, would be kc squared, partial hz by partial y, and already we said that hz is a sine kcy plus b cosine kcy. So by differentiating hz with respect to y, we have a kc outside here, and this kc would be eliminated with the square. So it would be minus j omega mu over kc, and here the derivative of sine it would be cosine, and the derivative of cosine would be minus sine. And this is Ex component of the transverse electric mode in parallel plate waveguide. Now the EX component is tangential to the plates. So by applying the boundary condition that the tangential electric field is 0, we can say that EX equals 0 at Y equals 0, the lower plane, and at Y equal D, the upper plane. At Y equals 0, by applying here 0, so sine 0 is 0, it would be A multiplied by cosine 0 would be unity, multiplied by this factor. This should be 0. Omega mu is a constant, and Kc is another constant which is not 0. And cosine 0 is unity. So the only term here is A. So A must be 0 to satisfy the boundary condition at Y equals 0. On the other hand, already we have now A equals 0. On the other hand, at Y equal D, we have minus J omega mu over Kc multiplied by minus B sine Kc D. Now we have two options, either B equals 0, and this is not accepted because in this case both A and B would be 0, there is no fields at all, or sine KCD, it would be 0. This is the accepted solution. So sine KCD equals 0. It means that Kc would be N pi over D, similar to the case of the transverse magnetic modes in parallel plate waveguide. Okay, where N here starts from 1, 1, 2, 3. Why? Because if I'm starting from N equals 0, if I have N equals 0, in this case, if N equals 0, I have B equal cosine Kc. I have N equals 0, the electric field Ex would be 0 and Hy would be 0. So I don't have neither Ex or Hy. If N equals 0, if I'm applying N equals 0, sine 0, it would be 0. So we don't have Ex, we don't have Hy. So for TE mode, we are starting from N equal 1. If I'm saying 1 pi over D multiplied by Y, so for any value of Y instead of 0 or D, we have a magnitude for Ex. But if I'm assuming that N equals 0, at any point for Y, the electric field would be 0, and this is not accepted. Okay? So in this case, the coefficient A would be 0, and Kc would be N pi over D, where N equals 1, 2, 3, and so on. So by applying these two conditions on Hz, we can say that Hz would equal B cosine N pi over dy e to the power minus j beta z. Now we could determine the complete form for the longitudinal magnetic field. His cosine function, and the value of Kc is N pi over D, and N equals 1, 2, 3, and so on. From Hz, we can determine Hx, Hy, Ex, Ey. So by applying the field components for the transverse electric components and using this value of Hz, we can obtain Ex as minus j omega over Kc squared partial Hz by partial y. Partial Hz by partial y, it would be minus sine N by y over t. And already we have minus, it would be positive j omega mu over kc, because n by y over d is kc, so it will be eliminated with this square. B sine n by y over d e to the power minus j beta z. In a similar way, hy would be minus j beta over kc squared, partial hz by partial y. Partial hz by partial y, it would be kc, eliminated with the square. And we have negative here because this cosine, its derivative would be minus sine j beta over kc bn sine n by y over d e to the power minus j beta z. And ey and hx are proportional to the derivative with respect to x, would be 0. So these are the field components of the TE mode of parallel plate waveguide. From this field component, we can see that Ex over Hy equal the wave impedance for the TE mode, and in this case it would be omega mu over beta, which equals k eta over beta, and the cutoff wave number Kc equals n by over d, where n equal 1, 2, 3, and so on. From the cutoff wave number, we can determine the cutoff frequency Fc. Cut frequency of TE mode is n over 2d square root mu epsilon. And it should be noted here that the lowest cutoff frequency is not 0, as in the case of TM mode, means that the TE mode does not propagate from starting from DC, should have a higher frequency to be propagating, and the propagation constant beta equals square root k squared minus n by over d, which is kc squared. And if n equals 0, then Ex and Hy equal 0. This means that there is no TE0 mode. So the starting mode for TE mode is TE1 mode. Okay. In a similar way, we can calculate the attenuation coefficient due to the conductor loss for the TE mode in parallel plate waveguide. At the beginning, we are going to calculate the transmitted power. B naught would be half real the integration of E cross H conjugate dot Z dy dx, where dy dx is the integration on the cross section area of the waveguides. In this case, the electric field component is Ex and the magnetic field component Hy and Hz. Ex cross Hy would be in Z direction, but Ex cross Hz it would be in Y direction, so it will not contribute in the power transmitting through the waveguide. So the power transmitting through the waveguide would be Ex multiplied by Hy conjugate in Z direction. So Z dot Z would be unity, and this power density would be integrated with respect to Y and X. So it would be half real the integration of Ex Hy conjugate dy dx, and the limits of integration for Y from 0 to D, and for X from 0 to W. Now, by multiplying this by the conjugate of this, J multiplied by minus J would be unity. E to the power minus J beta Z multiplied by E to the power J beta Z would be unity. Here we have omega mu beta over kc squared bn squared sine squared n by y over d. Okay. Omega mu over kc squared b squared and real beta. The integration with respect to x would be w. The integration of sine squared n by y over d from 0 to D, it would be D over 2. And already we have 2, so it would be D over 4. And it should be noted here, N is always greater than 0. There is no solution for N equals 0. So this is the power transmitted through the parallel plate waveguide for the TE mode. The power losses would be 2 RS over 2 multiplied by the surface current squared dx, and the surface current squared here would be Hz squared. The magnetic field in Z would correspond to the surface current. Hy is normal to the plate, it is not tangential to the plate. So the current density on the plate is proportional to the tangential magnetic field on the plate. The tangential magnetic field on the plate is Hz. So in this case it would be B squared cosine squared N by Y over D. Okay, and the value of Y is D, so cosine N by is unity, so it is B squared. So the value here is B squared, and B squared multiplied by R surface. B squared multiplied by R surface multiplied by W. B squared multiplied by R surface multiplied by W. Okay, B squared, we divide power losses over 2B naught. B squared will be eliminated with B squared. Rs is Rs. W will be eliminated with W. So the remaining part, it would be 2kc squared, because already we have 2 here. So 4 over 2, it would be 2kc squared R surface over omega mu beta D. W already eliminated, and real beta here. So this is beta. So the attenuation coefficient due to the conductor loss in the case of TE mode is 2kc squared R surface over omega mu beta D. This omega mu can be replaced by K multiplied by eta. So in this case it would be 2kc squared R surface over K beta eta D, never will be. Once again, if we are interested in calculating the total attenuation coefficient, it would be the attenuation coefficient due to the conductor loss plus the attenuation coefficient due to the dielectric loss. By comparing the attenuation coefficient for the different modes in parallel plate waveguide, we see that this is the attenuation coefficient for the transverse electromagnetic mode. The attenuation coefficient for the conductor loss for the transverse magnetic mode 1, and the attenuation coefficient due to the transverse electric 1. It can be noted here that the transverse electric 1 has less attenuation compared to both TEM and TM, especially after the cutoff frequency. Below the cutoff frequency or near the cutoff frequency, we have very high attenuation. But above the cutoff frequency, at frequency greater than the cutoff frequency, the attenuation or the conductor loss due to the transverse electric mode is much smaller than the transverse electromagnetic mode, and the transverse electromagnetic mode is nearly constant, is independent of frequency, but the transverse magnetic mode is the highest one. And this can be represented from the equations. For the TM mode, it was 2kRs over beta eta d, where here it was 2k cutoff squared over k. So in this case, the attenuation coefficient is proportional to the frequency. Here the attenuation coefficient is inversely proportional to the frequency. Okay? Alright. And in the case of transverse electromagnetic, the attenuation coefficient due to the conductor loss is nearly independent on the frequency, and all of them are proportional to the surface resistance Rs. Okay? Alright.